been doing review slash preview. So review of linear algebra or linear part of pre-calculus. That's what we have been doing, and a little bit of preview of how more advanced things will appear later on. So this definitely was a little bit of a preview because we have introduced, if not introduced, we at least pointed out the new ideas of vectors, as you can see on the left, as well as matrices. On the right, how we collect those numbers from the system of linear equations, and put them together in the form of two vectors in one matrix. Okay, so we'll be expanding this further into high dimensions. That's what the most of the course will be about. But a little bit more of a preview here of where we're going to go from here is just to look at once again. I will keep coming here to the one-dimensional case. The idea is to make the high-dimensional case, n-dimensional case, as close to the really simple case of one-dimensional as much as possible. So the solution is, let's step back to that, and it seems such an easy solution, but just to say that x is equal to b over m if m is not equal to 0. Okay, so that would be almost the complete solution of this equation, of linear equation of dimension 1. However, now we twist it a little bit in light of new problems that we're facing, high-dimensional problems, and make things more complicated. Might be unjustifiably so in this simple case, but really it is worthwhile. And the idea is to think of m not as a number, but rather as a function. Okay, what we're looking at is mx is, in fact, mx is what mx is. No, so forget about b for the time being. What is mx?
Line.
It is a line. It is m is a slope, but it is a function. It is a function. In fact, it is a linear function, but most importantly, it is a function. So you just y equal mx. So what does this function do? It takes x and multiplies it by m. Okay, so then the solution can also be interpreted then mx equal to b. Now, well, let's call that function f. Okay, then my equation mx equal to b becomes the equation mx equal to b. How do we solve those equations? F of x equal to b, how do I find x? What? Inverse, right. That's it. X equal f inverse of b. There is the inverse. As long as m is not equal to 0, there is an inverse. We know what it is. It is simply it is simply division by m. Okay. So, and that's kind of a more advanced way of looking at this really simple problem. So, thinking about the left-hand side as a function, while the right-hand side is the value of that function, and we are solving the problem. That's what equations frequently are. Is solving the problem in reverse. So you know the function and you know the output of that function, which is b. Now you want to find the input that gives you that output. So once again, b is the output, known, x is the input, unknown, and m is also known. M is a function. Okay? So, and then we solve this problem just as many other functions. So you can think about, say, ex is equal to 3. How do I solve it? I apply the inverse. So ex is equal to 3. What's the solution? X equal ln 3. Okay, so that's the same idea. I'm just bringing this nonlinear example in order to illustrate the idea that how to deal with inverses, how solving certain equations, the simplest kind, is done by finding the inverse function. Okay, so once you know the inverse function, that's the good news, by the way. Now, what if I have here, instead of 3, I have 5? Well, this doesn't make any difference. I already know the inverse. I know the logarithm is the inverse, so I can put any number in the right-hand side of my equation. It doesn't matter what my output is. For any output, I can find the x that I'm looking for, right? Because the inverse already has been found. So the key is actually finding the inverse, and that's what you do in pre-calculus. So you have exponential function, and then what you find the inverse, and then you're done for like forever. Any kind of equation like that can be solved. Okay, so we are about after the same, except now it is even simpler than that. All we do is multiply by a number. Okay, so that's my linear function. It simply multiplies. So f of x is equal to actually over here. The function that we're looking at is mx. That's my linear function. And once again, how do I solve the problem x equal to b? I find the inverse of this function. We already have. It's simply division by m, and that's it. So f inverse of x is equal to x over m. It works out. Remember, linear functions are invertible as long as m is not equal to 0. Okay, so that's how you look at this very elementary situation. It comes very handy, that approach, when you go to high dimensions. So let's just take that for a moment. The equation that we're looking at is this at the bottom, x equal to b. And once again, we're not thinking of this as a multiplication, even though we will be referring to the separation over here routinely as multiplication. But what it really is a function. So that matrix A is just a matrix itself, and nothing but a compact way of collecting the data that makes up a function. Just like that function over here, f of x equal to m, I could just say, well, f of x is equal to mx. I could say it is represented by a matrix, 1 by 1 matrix. Okay? So in one-dimensional case, you have one-dimensional input, one-dimensional output, so the whole data for your linear function is one single number, that is m, and so I create a 1 by 1 matrix. Okay? In dimension 2, things become complicated. As you can see, we have two-dimensional input, two-dimensional output, so you need total 4 numbers, and you put them in that table over there, right here. But it doesn't change the fact that the matrix operates as a function. So what we're looking here is, on the left we have input, b on the right we have output, and this one is a function. Okay? And then once again, so what do we do? How do we solve this problem once and for all? X is equal to what? A inverse B. Okay, so only the thing that we need to do is to figure out what is that matrix, the inverse of a matrix A. And that matrix serves as a function, okay, and then we need to find its inverse, and then we're done. So that's the idea of dealing with equations as well as the whole linear algebra is thinking about everything as more as functions than matrices, and the function is solved in this manner. Not every matrix naturally has the inverse, just as not m has to be not equal to 0 in order for us to have the inverse. Similar situation happens in two dimensions. You might remember what the answer to this question is. When is the matrix? When does the equation system of two equations has a solution? Well, say x plus y is equal to 1. Remember this one. X plus 1 is equal to 2, right? So my matrix is 1, 1, 1, 1. What can you say about this matrix based on the look carefully at the system of equations? What's so special about the system in the first place? No. 1 and 2. It's not the same equation. No solution. Okay. No solution. What does it tell you about the matrix? What? It is not invertible indeed. So if we can invert, it works out. So if there is an inverse, we can always find the answer. So if there is no answer, we know that it is not invertible. So a function that has, remember, the only situation, bad situation like this in dimension 1 is m equal to 0. This one has no zeros whatsoever. It says 1, 1, 1, 1, and yet the matrix is not invertible. So that function represented by this matrix, in fact, has no inverse. Okay, so then there's a way to determine ahead of time when the function is invertible or not. It is determined by, I wonder if it is, so whether it is invertible is determined by its, never heard this word, is determined by its determinant. Determinant, which is determinant of A, dt, in this particular case, matrix of a matrix, say A, B, C, D, is AD minus BC. Okay, so as you can see in the particular case of that example 1, 1, 1, 1, 1, 1, 1, it is equal to 0. When determinant is equal to 0, the matrix is not invertible. Okay, so that is a preview. So vectors, dimension 1 is a number. Dimension 2 is a pair. It is located on the plane. In dimension 3, it is located in a three-dimensional space. Beyond that dimension, we cannot visualize it, so it's not tangible anymore. Second, we are looking at here as matrices. We are thinking of matrices, and then in dimension 1, it is simply one number. In dimension 2, it is 4 numbers, and so on. In 3, it will be 3 by 3 matrix. Okay, so more and more complexity increases quadratically. So dimension n, a table will be n by n. How many entries? N squared. So complexity increases. The problem is solved by means of inverting a matrix. The problem of solving a system of linear equations. So it is first expressed in terms of as an equation, matrix equation, but it is solved by finding the inverse of the matrix, if it is possible. The shortcut for determining whether it is possible is the determinant, which is a complicated computation based, it is kind of complicated. This is, when it is 2 by 2 is okay, when 3 by 3 it is already becomes cumbersome. But we certainly will have to face it. Okay? And that's the big part of the whole course is outlined right here on this page. So that ends the preview, and we're moving on to actual stuff, and we will do it gradually. Now all of these pieces appear together simultaneously, and we will try not to do too much at the same time. So at first we'll concentrate simply on x's. X's as in this particular case, x is a two-dimensional vector, and then we'll be just studying vectors to begin with. Okay, so that's the first topic, vectors in Euclidean spaces. Okay, so once again, what I just mentioned a minute ago, let's look at the Euclidean spaces in different dimensions, such as starting with a line, and then we impose on it. Remember, we started with that in the very first week. We impose on it a Cartesian system. So we take that line and sorry about that. It is actually does not have the end point. It does not have an arrow, so it's purely a line. It is purely a line, and then we impose on it extra stuff. We impose 0, we impose the arrow, and we impose units. Okay, so that creates a Cartesian system of dimension 1. And then we go on with the same plane, right? So plane like this, and we take that plane and put a what on an axis. Two axes, ideally they're perpendicular, and once again it creates a Cartesian system on that plane. So the plane is Euclidean. You know, Euclid, compare Euclid on one hand and Descartes on the other. So they're separated by, what is it, 1700 years. Right, so, okay, so they did not, Euclid did all this geometry, but he did not know Cartesian system. He did not know the anything of that kind. Space is even hard to visualize already on a piece of paper, and that's why, by the way, Euclid stuck for the most part with the plane geometry. 3D geometry is much more complicated, so I don't know. I'll just put something geometric figure here just to emphasize that's what we're talking about. But really, it becomes only manageable when we add the axes to our space, and then we can now record everything in that space. So this is the direction things proceed, both historically and I think it is easy to think about it from left to right. So first you understand the real line and the plane, like a plane as a piece of paper, nothing on it, and then you, if you want to really take it seriously, you can do triangles, you can do Pythagorean theorem, parallel lines, all of that business. But if you want to do analytical geometry, you want to do motion, you make calculus at some point, you need Cartesian. So all good. Unfortunately, that does not, the idea does not work out anymore because we are running out of our space is three-dimensional. So we cannot, there is nothing here for us to start with. We will have to go backwards. We will have to start with a system with each kind of a Cartesian, and then try to imagine what such a space would look like. Okay, so it becomes purely algebraic. Algebraic from algebra to geometry rather than vice versa. So this is geometry on left, pure geometry, and then you produce, with Cartesian system, you create algebra. Okay, so this is algebra for the most part. Algebra, and remember, we can do a lot of things with Cartesian system, including distances, as well as angles. Okay, but in dimension n, what do we do in dimension n? So if 1, 2, 3, n, what do we do? What is that? What are we studying in the first place? And the answer is it is strings of numbers. And those strings are pretty much those vectors. So you know that's it is not surprising that we are facing that, because that actually is predictable. If you follow the right column from dimension 1 to 2 to 3, you see how everything is represented by a string of numbers, whether it is a point or a vector. It is a string of numbers, 1, 2, and then 3. You can already guess that if you want to continue on with this, you will have a string of 9 numbers. And just to make sure that we're not making it up for no purpose at all, I think data, that's why we still want to do n-dimensional things, because data might be n-dimensional. So say you 100 numbers might appear in a different way. Either you conduct, say, 100 experiments or 100 measurements about something, and then you can, as many times as you repeat that computation, you'll produce 100 numbers. And so that if you, all possible outcomes will create 100 dimensional space for you. Or you look at the prices of commodities, and you have 1,000 commodities, and then each number could vary independently. That's the key. Of course, it's not just numbers that you're facing, but the numbers that are independent of each other. Okay, so look at x, y, z over there. You can move x, y's independently, y, and z, and that's what we're talking about. And so presumably, say price of gold and wheat might be changing independently, hypothetically, until proven otherwise. So, and then that creates possibly 1,000 dimensional space. So the notation then is R, R1, R2, Rn. X1, X2, well, I'm not going to use brackets just yet. I'm going to be sticking with horizontal representation. So you might remember a little bit about sequences from calculus. Have you seen sequences in calculus? Yeah, a little bit. So there are. We're not going to be worrying about infinite sequences, fortunately. So n will be always finite. So no concern about limits or anything like that. Just a sequence of numbers. That's how you write them. You have you have a letter that represents the name of the sequence, which is pretty much x, and then the superscript indicates the item on the list. So you can, just to illustrate this, say x, y, z is, we don't want to stop with this, even though we'll keep repeating, we'll keep coming back to lower dimensions, and we'll have x, y z is always again and again. But let's just keep in mind with the big picture. So x, y, z is really not. You know that you're going to run out of letters sooner or later. So you can just as well write it as x1, x2, x3, indicating that you have 3 numbers separated by commas. So it's 1, 2, 3. All of these are 3D vectors. And then you use the advantage of x, y, z over x1, x2, x3. It looks more cumbersome, but then at least you every time you know what you're talking about. You're talking about you know that is 3-dimensional. Okay, so all right. So once again, beyond dimension 3, virtually impossible to visualize. So what could even possibly be doing with these? And we could do a lot of things with that, because whatever we know about those on the left, whatever idea, geometric, algebraic, or otherwise idea that we see in our spaces, in our real space, on the either numbers or plane vectors or 3-dimensional vectors, whatever we can do with those, we can do with n-dimensional vectors as well. So for example, if we're talking about numbers, we can add them. Okay, so we can add vectors even though they are n-dimensional. If we can measure distance between 2 points, we can measure distance between points in the n-dimensional space. So if there are angles between vectors in these vectors, I can do them here. I cannot show them in n-dimensional space, but still we can compute angles between them if necessary. Okay, so let me be specific here. So I already wrote it, but let's say so Rn is the set of all ordered strings of n real numbers. Of course, the ordered, if it is a string, there is a presumption that there's an order of it. So it's not a bag of numbers, it is a string of numbers put in the particular order. Okay, so then certainly once again R1 is just numbers. It's a string of a single number like this. So that's all there is. So that's why we don't have to use the any kind of special notation. It's just numbers, real numbers. Okay, so let's start with a little bit of a structure of relative structure of these spaces. We'll refer to these as spaces of Euclidean spaces, and so you just omit Euclidean most of the time, and you just indicate the dimension, and then you know. Because Euclidean is a little bit misleading term because well, Euclid would not go beyond dimension 3, and there is nothing that we can think of specific corresponding idea to the idea of Rn, which is simply a string of n real numbers. So what is it? We can only try to imagine. But at least even n-dimensional space is made of lower dimensional spaces. So for example, you can see that the plane is made of lines, right? So for example, so the plane R2 is made of lines. Okay, so let me just illustrate. All we have to do is just to repeat one of the axes. So I take the horizontal axis and I have a bunch of them like this, right? There are others. Remember, certainly you remember that from pre-calculus, but this is the most obvious way to decompose the plane into lines. So as you can see, I speak of decomposition. Why? In what sense? In the sense that these lines are firstly parallel, so they don't intersect. First of all, they don't intersect, and second, they cover the whole thing. Okay, so that's a nice decomposition. All we have to do is just to repeat one of the x's. So let's make this algebraic. Okay, so horizontal line or lines is xy. So let's start using the set notation. So does it look familiar, this notation with the braces? Does it? Mm-hmm. So xy, so that's the so braces. Then xy, depending on the dimension, might be higher, but let's say dimension 2. So xy, which is a pair of numbers or a point on the plane, and then you impose following the column. We impose the condition. So for example, y equal to say r. So for every r, this is a horizontal line. Y equal r is this horizontal line, or r is how high it is located. Okay, so once again, it's not hard to see that they cannot intersect because they are parallel. They have all the same slope, and they cover the whole plane because, well, I hope that that is clear. And then similarly, a vertical line, xy. What is a vertical line? Yeah, let me pick a different letter. X equals S, so over all real S. And this is over all real R. So that gives you the whole thing. So each line and they represent. So each of these, that's the point I'm making, these are copies of R, right? So these horizontal, these lines are copies of R. So lower dimensional spaces make up high dimensional spaces. Okay? So that was dimension 1 versus dimension 1 versus dimension 2. Well, you can certainly okay, now what would be if we climb to the next level? So the statement is, the statement that we started with is this: the plane R2 is made of lines R. If we go to the next level, what's the analog?
Z.
What?
Z. Z. Z.
No, this statement.
R1, R2, and R1.
Start over. I didn't hear the beginning.
Is R3 made of R1 and R2?
Yeah, or you can go one or the other way. Yes, you can certainly make you can make you can make both statements. So let's make both. Why not? So so the first statement will be the space, the three-dimensional space R3 is made of copies of R1, the line, but it can also be made of copies of R2, the plane. So many planes or many lines. I'm not even sure which one is easier. No, I think the last one is easier. So let's make the space of planes. So how would you do it? Can you think of a picture similar to this one?
Feel like if you just took the top part of the cube
Okay, and
and just had a bunch of them.
yeah. So yeah, you have a plane, and you sort of translate that is them vertically, like this. So a bunch of vertical planes, horizontal planes. They will make up. It's like a book, right? It's made of pages. So pages, we're thinking of pages if we think of them as planes. They're one-dimensional, two-dimensional, but together they will make a three-dimensional book if you have enough of them. So that's what I'm talking about. The equations will be almost the same. The horizontal plane will be x, y, z with z equal to r. Okay, so that's how far the elevation of that plane is. And then, so it makes up the whole thing, but you can certainly pick, instead of z, pick y, and you pick x. So with the choice of x is usually located like this, I already took care of representing the space as made of planes, not just horizontal, they are parallel to the xy plane, but you can also pick planes parallel to xz plane. So like this. As many as necessary with all closeness. So these are not only they're parallel to the z, parallel to the xz plane, and they also perpendicular to the y-axis. Okay, so one remains, and that is what remains. YZ, that's right. So they will be kind of facing us like this. Okay, so these are simply y equal to say s, and this is x equal to say p or something like that. So these very simple equations represent plane parallel to the coordinate planes. Okay, so this is parallel to xy plane, and this one is parallel to xz plane. Okay, so that's as you can see, we have more and more dimensions because it took us only two statements like that, only two ways to decompose, two axes, two ways to decompose the plane, and now we have three ways because we have three different coordinate planes. Along to each of the three, we can decompose our space into this kind of books. Okay, now the first state, this one. Can you think of how we represent our three in terms of lines? Well, it's not different from, think about it. We know, according to this picture, we know how to represent planes as in terms of lines. And we have represented our space in terms of planes. So space in terms of planes, planes in terms of lines, right? So I could just take those and mimic what I have right there at the top, and I could put it like this. each plane will be decomposed into lines. So this way I choose certainly different ways to do it, but these are parallel. These lines are parallel to the y-axis. Okay, and then I could do this way. I could do it, and then I could go vertically, and once again it will be fully decomposed. So these are the simplest lower dimensional spaces that we can actually see. But you can, if we try to take it this analogy, that's what it is, to the n-dimensional case, n-dimensional space, then in a similar way, you can represent. You can still decompose that n-dimensional space that we cannot see nor touch. We can decompose into smaller spaces that are all manageable. So, for example, starting with the very low dimension, we can represent it as in terms of lines, right? So there will be there are n axes in the n-dimensional space. You just take a line that parallel to. You pick one of the axes. And then you take all the lines parallel to that. So imagine that parallel to that axis, and then you will cover the whole space. But you can do the same with planes. Okay, so once again, planes, and you can now that's slightly harder to imagine. But try to decompose try to think the other way around. So here we started with the three-dimensional space, and then we decomposed it into planes, for example. Okay, but doesn't help if you go backwards. So suppose you don't understand the four-dimensional space, but you do understand the third-dimensional space, and you know that the form is made of the ladder. So can you imagine anything helpful from this idea? It's a stack of three-dimensional spaces. That's what four-dimensional space is. Of course, you cannot stack it in the literal sense. You need the fourth dimension, but those three-dimensional spaces are close to each other, just like those planes. Okay, so you need the fourth dimension in order to penetrate to move from one three-dimensional space to the next. Okay, so if you can imagine that, you are on the right track. But the idea is, if you cannot, you imagine that, then that's okay. That's what algebra is for. We can always go back to algebra and solve that a problem that we face algebraically. So let's do what we did last time. We started last week, and that is the distance formula, and just distances in the spaces 1, 2, 3, n-dimensional spaces. Okay, so distances. Just to see that n-dimensional spaces are nothing special about them. We can do everything we can do in low dimension. We can do n-dimensional spaces, so including distances. Okay, so all we need is the analogy is I hope we already did a little bit of work. That way, it is a repeated application of the Pythagorean theorem. So starting with this. Remember this discussion. So how to express the distance? We are not measuring distances, right? I mean, think about it. If we did not measure distances on the plane, and we wanted to use the distance formula, then imagine now we are dealing with n-dimensional space. We cannot live there, so there is no n-dimensional, tape to measure distance in n-dimensional space. All we have are, in fact, those strings of numbers, and those strings are those numbers are the coordinates. So you have to express those coordinates in terms of you want to express those distances in terms of those coordinates. So that's it, right? So we have 2 points. Okay, this one say x1, x2. Let's just for the sake of n-dimensional idea, will be even though these are xy plane, if this is xy plane clearly, I'll try to use a little bit the notation with subscripts to indicate the dimension clearly. So that point in blue has coordinates x1, x2. So this one is x1 and this is x2. Okay, and then Oh, you know I don't like x here. How about I put a instead of x? So the x's are called, this is x1 and this is x2. The names of the x's rather than x and y, we have x1 and x2. And then I could name my point a1, a2 with coordinates a1 and 2, and the second one, this will be b1, b2. b1, b2. So once again, it seems those subscripts make things more cumbersome, but it pays off when you move on to high dimensions. Okay, so it works, and some of the formulas are just you will be able to recognize symmetry, and kind of things will become more predictable. So anyway, so back to the distance formula that we already did once. So this is the distance we're interested in, and based on what? On the correspondence between the Euclidean distance on the plane. We know how to measure it like this, and we have expressed this distance in terms of with the Pythagorean theorem. We expressed it in terms of the coordinates. So it will be b1 minus a1 squared by the Pythagorean theorem, right? And b2 minus a2 squared. This is literally the Pythagorean theorem where my triangle is my right triangle is this. So choosing the axes perpendicular to each other is a natural choice, so that Pythagorean theorem applies. On the other hand, if in n dimension there's no geometry to rely on, so we'll just assume that that's just the way it works out. The way it works out in lower dimensions will just translate into the idea of what a thing's supposed to be in high dimensions. Okay, so that's the Pythagorean theorem. The distance is found. I take a square root, so it gives me the distance formula. Okay, so now what I do is I take that picture and moving to the next dimension. So this is n equal 2. In n equal 1, by the way, the distance is simply equal to the absolute value of, say, b1 minus a1. I'm not sure if I need to go over this one more time. On the line, every point is represented by a single number. The distance, to find the distance between them, all you have to do is just subtract and take the absolute value. Okay, that's what I have here. This is dimension 2. Moving to dimension 3, there will be one more x's and one more for degree of freedom. So it will not be, well, this actually is helpful, is to think about this less as a triangle, but rather as a square, like this. It is a square, and we're talking about the diagonal, no, not a square, rectangle. So when we're talking about the diagonal, the length, the diagonal of the square with these sides. I'm sorry, not square again, rectangle. So these sides, right? Look at it. So one side from b1a1, b2a2 for the other side, and what we're looking at is diagonal. So we don't want to go like this. We're going straight. Okay, and so that gives us the Euclidean the distance formula, and it is also known as the Euclidean distance. So, and we are translating this gradually into higher dimensions, and we'll be discovering, and then we'll just by sheer will, we'll just say, well, this formula will be applicable to n dimension as well. Okay. This is mathematics. If I want a particular formula to be true, then well, I just say it's to be true. I use it as a definition. That's a trick. So this one is still a theorem. Why? Because we have to compare the Cartesian system with the Euclidean geometry. But beyond the high dimensions, there is no Euclidean geometry to speak of. So we'll just using these ideas as definitions. But first, let me once again illustrate this idea that in 3 dimensions first. Once again, it's still geometric, still Euclidean geometry still applies. and we want to know the distance between these 2 points, like this. Okay, so each point is represented by coordinates. So this one is A1, A2, A3, and this one is B1, B2, B3. Okay, so we can guess, and we did that we can guess what the so that distance is. We can guess what the answer is supposed to be. So that's the length of the diagonal, that red diagonal over there, is equal to B1 minus A1 squared plus B2 minus A2 squared plus B3 minus A3 squared. Okay, with the coordinates, I didn't draw the axes, but so if you that's let me try to do that. Axes maybe there, like this. C, X, and Y. Okay, so that's not quite what I had in mind. Oops. Let's move them somewhere. Okay, so these are my x's, and this cube, this box, is hovering, and then the point, each point has 3 coordinates. They're kind of far, but let's see. This one point, I'll make it orange. This is then A1, A2, A3, and then there is the other one over here. Let me try to imagine where it is. So it is higher. So B3 is here. It is lying higher, but more to the, well, let's say this is B2, and this appears to be B3, B1. Okay. So as you can see, these are the sides. These are the 3 sides of my box. Okay, and so then once again, this idea applies here, except it's the diagonal, not a rectangle with these 2 sides, but rather it is the diagonal of the box with these sides, 3 sides. So if it was 2 here for a rectangle, now we have a box of 3 sides, but still diagonal. So you certainly can confirm with a, well, probably we'll need a better picture here, but it is certainly doable. And if you do need a better picture, you probably you can simplify to something like this: a picture of a, I don't want to slow it out of time. So the picture of when one of the points is simply the origin. Okay, so I move the that point to the initial point is here at the origin, and the end point is the opposite, like this. Okay, so then the formula works out. We'll do a little bit of that next time, and then we'll continue on. Okay, so once again, homework will be assigned tonight.